Yeah, hello everybody to our lecture in statistics. First of all, yeah, tomorrow I give you then the organization for our talks on this weekend, Friday, Saturday. So we will meet in the afternoon. I think we can then start at around 14 at Friday, and we will end then around noon on Saturday, and we will go to Jever there in the youth hostel. And I don't know if everybody from you knows Jever. I know somebody of you went to school there, of course, but maybe we can go also then downtown and just have a look at Jever, because Jever is also directly related to statistics. What we have done here is that do you know who has invented these calculations of linear approximation? Well, if one has no idea who has done it in mathematics, then a good choice is always to take Carl Friedrich Gauss, because he more or less invented almost everything related to modern mathematics, or has written at least something about this. But in this case, he really invented this method because yeah, he was asked by his earl in order to yeah, to categorize the land up here. And so he just traveled around and then he took always some point where he could look very far away in order to measure distances from different points. And this was the method of triangulation in order to obtain a good map of the land. And of course, if you are measuring the distances from different points, then of course you do not get a cut of every, so to speak, 3 points where you are measuring, though you are always, if you take the data, you obtain not only one point where all the lines are intersecting, but you have always some error in the measuring. And in order to then minimize more or less his overall error, he invented the method of these yeah, linear regression. And in the region here, he used one point at the windmill in Farel. Maybe you were there already. They have a very large Dutch windmill. And the other point was the castle tower of the castle of Jever, which he used in order to measure the distances here in the region. And yeah, maybe we can also visit the castle in Jever. Okay, but today we will leave the linear regression, and for the end, I come back, so to speak, to purely descriptive statistics. And what I want to do with you is to talk about some simple methods of forecasting. And here are some quotes. One of maybe one of the most famous physicists of the last century, Niels Bohr. Prediction is very difficult, especially if it's about the future. So with a smile, or from Winston Churchill, I found, do not believe any statistic that you haven't forged by yourself. So don't believe your only believe your own data, so to speak. Then you know the outcome. But anyhow, we want to talk about simple methods of forecasting if we have some data. And for this, we more or less look at in general how, of course, also in or especially in economics, if we take especially data developing over time, thinking about the development of revenue, of profits, of costs, then in general, in economic data, we can sometimes try to split off the data in different patterns. And I'm a macroeconomist, so then you quite often have the long run view. So in general, of course, more or less every company is depending on the general circumstances of the market or of the country or the economic region you are doing your business. So in general, if your region is performing quite well, then the probability that your company is also performing, at least in the long run, similarly to the whole region, is also highly probable. So in general, we can think of that we have an underlying long-term trend in our data if we look, for example, at revenue or profits. How does it develop during the last 10 years or something like this? So this would be then some long-run trend. Then also, of course, this finds you in macroeconomics, but you find this also in a smaller case, if you look at some special market, that within a market you will, if you go further back in history, that you find there some cycles similar to a business cycle that you have within this market. Over some time it goes up and then it goes down, and afterwards it goes up again. And we don't know the frequency definitely from these cycles, but we can look at our data that maybe we can identify this frequency. And this, of course, will be then also a very useful information if you could identify such a frequency, because then maybe you know if you are just in an upswing or in a downswing. And what is always very important, and there you can also, of course, think about investment at the financial markets. The points where you are really very highly interested is, of course, always these turning points here. When it's going down again, or when does it go up again? And then if we have a look outside, then you see that it is raining. And especially here in Europe, we are, of course, also highly depending on, within a year, especially at some seasonality. And if I remember it right, we have in this course also some students studying tourism. And of course, the tourism sector is, of course, one of the main examples where you have this high dependence on seasonality, if you are in winter or if you are in summer. If you have a company which does its tourism mainly on winter sports or something, then you are here in the part where you have an upswing, and here at the coast, then yeah, we don't have that much tourists during winter time. And this just depends more or less on the seasons, on the weather. And so this is, of course, also something like a cycle, but yeah, this cycle we can better determine than such a general economic cycle, because this cycle we know from, yeah, the weather data, and this we know at least not the weather tomorrow, but in general we know that in wintertime it's colder than in summertime. So then we can also try to filter our data in order to determine some seasonality component. Well, and in the end, of course, we have to admit the future is unsecure. Of course, we will have also something like a random component which we cannot forecast or which we cannot determine. And well, the green line up here, this is yeah, just a data series which I created, and this data series is just the sum of these 4 other data series. And as you have seen within this course, I always, yeah, try to do also a practical part. And for this, don't misunderstand me, but so let's try to create such a data series with these different components. And now we come, so to speak, from the other side. We start with a long-term trend, then we want to create a long-term cycle, then a seasonal cycle, and in the end a random variable, because yeah, this has also some utility, because then I hope that you get a feeling how to look at these components. And of course, if we find a technically created data series which is quite good fitting our true data, then of course we also can start to make a regression between these and start to test it statistically. Okay, then let's at first make it a bit larger, let you see more. And let's take here time, and let's take here the trend, and yeah, let's start from 0 and just in time. Yeah, let's take more or less something like 1 year. So we can think of that we have, or let's take 2 years. Sit until 48, yep. So in this case, more or less, then we could think we have something like monthly data. And yeah, then let's try to start a long-term trend. kind of function would we use for a long-term trend? And of course, we are in economics, and what we are very often interested in economics, or what we quite often assume in the long-term development of economic variables. How do we develop? And this is even when you look at a company and they make a press conference, then they make a long-term statement, and then they announce something. We assume that for the next 5 years, our company is on average developing with what? Let's take also the chat. If you think, for example, something like revenue or profits or costs, costs not, because hopefully they are not increasing that much. Well, if we take a long-term trend, then quite often you assume for the next 5 years, or you make your projection that more or less our target is to grow in revenue by 4 or 5% or something like this. Okay, this is quite often, if you read some forecasts of a company, this is our aim. Our aim is to have a growth rate per year of, let's say, 5% next year. So maybe think of this if you read the next X statement of Elon Musk about some of his companies, maybe. So long-term trend often means on average we assume a constant growth rate over time. So which kind of function do we use when we are assuming a constant growth rate? Think of the continuous case. This I also have to mention that we, yep. Yes, this is possible. This would be then a geometric growth, and if you go then to, but then you have a discrete function, then you have, of course, in the discrete case, we would have AT plus 1 is AT times 1 plus G to the power of T. This, I think, you have also seen in mathematics when you had investment processes and interest rate processes and so on. And if we translate this in continuous time, you haven't done this in mathematics? No? Because in this case, when you ask in general, then we would say, if we say this would be interest rates, then you say you start with per annum, so per year interest rates, and then you cut down the period to quarters, to months, to day, to seconds, and so on. So this then would mean that we divide this by n, and we divide the growth rate by n, and then we let move n to infinity, so that the time interval gets smaller and smaller and smaller. And well, then you can in general show that this function becomes the exponential function. So in continuous time, this would be then a of t equals a0 times the exponential function done with some growth rate gamma times t. Hopefully you remember this, that this function e gamma t a0 looks just like this. So what we then need is that we just make some two assumptions about the parameter a and about the parameter of our growth rate. So what we need is, since I need some more lines, so this would be then a0. Let's start just with 1 and gamma, and this would be our growth rate, and let's also start here with 1. And then we just put it here, a0, fixing again, times the exponential function of gamma. This should be constant, so it has always to read in for every calculation, and then we start at t equals to 0. And this should then last until our two years. Let's see how it looks like. So, and here you see that in this exposition 48, then of course your exponential function after a while speeds up very fast, and for this then that we, so to speak, see a little bit more. Let's change especially here our growth rate, and then we will see that the curvature is not that strong anymore. So then this looks maybe a little bit nicer. Let's take maybe also here 0.05. So this would be then our long-term trend data. So, and then let's take our cycle data. take for the functions red. What kind of function would we use for cyclical data? So what we want to model is just such a pattern. Yep. Okay, this would be possible. Yeah, it is. It is okay. What we actually can say is, and this is actually also done by fitting data, is that in general, and maybe you think about this, maybe in class 12 or 13, you have talked about this in school, that every, so to speak, usual function you can approximate with a polynomial. So with a plus bx plus bx squared c x to the power of 3 and so on and so on and so on. And of course, we can also always use a polynomial to some power of 8 or something to highly fit our data. This is always possible. But maybe we can think of another function which directly, because then if we take the exponent, a polynomial of 3, we really have to play around with the parameters a, b, and c in order to obtain such a pattern. But do you remember some function which directly has this pattern? So maybe you remember from school. Yes, that's definitely right. And what is the sine or the cosine? This is just coming from this circle, and then, like on a clock, you just let's move this line around this circle, and then the length here is sine, and the length here, this is the cosine. And of course, this is a rectangular triangle, and from this definition, of course, you have cosine squared plus sine squared equals 1, and this is nothing else than some special case from the Pythagorean theorem that the two short sides of a rectangular, the squares about this, equal just the long side. Well, of course, we also have to define that the radius of this circle is just 1. Well, and then you can think of that if you start with the horizontal line, then you have 0, and then if you have moved 90 degrees, then you have your first maximum. If you are at the other side, then you have 0 again. Then you have a minimum, just the opposite in the minus region, and you come back to 0 again. Okay, and then of course we can move these extremas up and down if we just put in front of our sine function again some parameter, as we did it here, where we said this would be a 0 times exp of gamma t. So then let's do this. Let's call this then the parameter in front of our sine function b0. Let's also start with 1. And then, of course, in order to define the frequency or the period of our function, this would mean that we then just divide our time parameter by some other parameter. So here we can use the sine of x function, and in order to move it to get a higher maximum, we put in front that we say bt is some parameter b0 in front of this function, and then we put here t over some parameter small b. Let's take this, and in order to feed in this in our software package, hopefully you remember also that we defined in mathematics that the number pi equals 3.14. We define this as 180 degrees. So this means, since we know that sine of 0 degrees is 0, sine of pi half is 1, sine of pi is 0 again, sine of 3/2 pi is -1, and sine of 2 pi. So the full circle, therefore we call this the full circle is 0 again. So here you have pi, 2 pi, 3/2 pi, and 1/2 pi, 1 and -1. And this looks like this. So for this, then I put in front of our function now 2 pi ups, because all integers of 2 pi means that I'm moving one full cycle in time. So 0, then 1 pi, 2 pi means I have finished one full cycle, and then 4 pi means I have finished the other one, 6 pi, and so on. Okay, so if you have this picture in behind, that a full cycle is just moving in degrees, 360 degrees, and this is then translated in with relation to this circle number. Okay, then let's use also B0. Let's also start with 1. And this would be then the cycle. And then let's take B0 times the sine of 2 times, and to read in pi means just writing pi times brackets behind, times our t over B0. So hopefully, here I missed one bracket. This not equal, no equal sign. This should be hopefully 0, of course. Then here we are starting, and if I go now on to 1, since I multiplied the parameter t with 2 pi, this should also be 0. Well, almost here you see that Excel is calculating this sine function via an approximation, and therefore you don't obtain a 0, but almost a 0, a number up to minus 16. So here you see that in the end, your software is has somehow to calculate the numbers, and I think yeah, Excel is calculating up to, in general, if you don't change anything within the setup, up to 15 or 16 digits. And then for this, you find here an error in the calculation, because of course there should be a 0, because this is just sinus of 2 pi, and this is sinus of 4 pi. So let's maybe also write this down here. So equals pi. Here you see the 3.14. And of course, since this number does not go to infinity in the digits, and then you don't feed in the theoretical value within the function, it has to be different from 0. Okay? So, but then let's say, let's interpret our 48 data points in time as monthly data, so 2 years. And then let's say that we want to create cyclical data with a cycle of 2 years. Okay? And for this, we then have to divide, I think, by 48. And then our numbers, and let's move it down. 48, 2, or 96, I don't know right now. So let's feed in this data. So here the cycle, and then this. And then you see, okay, we have now here a 2-year cycle of our data. And later on, of course, then we can play around with the parameters. So what else? Then we want to have the season. But well, let's increase the number of data points, because if we want to interpret as monthly data, then we just would have to create now a season, or let's say let's interpret this as quarterly data. This is maybe better, because otherwise we would have a 2-year cycle, and then if we want to interpret as our seasonally data, then we would have just a 1-year cycle, and then we don't see that much. So, but if we interpret this as quarterly data, then we would say that a season returns every 4 data points. So, and maybe for our seasonally data, we could say that we just, fit here for seasonally data just a pattern which occurs always in the same way after 4 data points. So in this case, seasonally data, there we could say that A4 equals A0 or A t plus 4, so to speak. Oops. A t plus 4 equals AT A t plus 5. No, not AT plus 1, AT plus 6, AT plus 2, and AT plus 7, AT time plus 3. So we fix just A0, or no, let's take the A we have already used. Let's take the letter C, 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 C0, C1, C2, and D3. So, and then I ask, do I have some of the tourism guys? So should we take a winter tourism company, or should we take a summer tourism company? So in one case, if we would say that we start in winter at T0, then we would have here a high revenue, and then going down and coming back again in autumn, or the other way around. This you can choose. Or let's say, no, let's say we start in spring. So let's say this is spring, summer, autumn, and winter. What kind of company shall we take? Or you can choose it too. Are you skiing? So then let's take winter. So this would then mean, in this case, 1, 2, 1, 2, 3, 4. Then I need another one here. Okay. So then maybe we come from a quite high number. Let's say, oh, I even need another one here if we want to play around with this. So let's say we come from 1, from 3, then 1, then maybe -1, and in winter time we have 5. And in order to play around in a minute with the data, I also introduce up here another parameter, and for the starting point, then we just multiply our seasonal components with this parameter, because then I can move up or down the seasonal component just by moving up and down this parameter here. So if I put here 0.1, then you just see that your seasonal component is going down. But now we have to use it for the rest of the data, and this we then have to copy downward. So let's see how this data looks like. And this is now, oh, sorry. Add data, season, and this one. So, and so this looks down, 1. This looks not that nice because I have here just chosen by accident a linear line. So let's say in spring we have also some business on Eastern in our touristic sector, so that we do not have here a linear line by going down in the revenue. Okay, and the last one would be then our random component. And yeah, I don't know if I already have shown this, but in Excel you have the function random variable, or in German Zufallszahl. And if you then just press enter, then he creates you a random number between 0 and 1. Well, and maybe here we want to have also a random component, which is just symmetrically around 0 and 1. And for this, we would then just subtract 0.5 because then you will have just a random variable between the interval of minus 0.5 and plus 0.5. And of course, when we want to play around how large is the impact of our random variable, we can also put in front of our function just one parameter. And this we will call d0. And so let's put in here d0, fixing it times, oops, this random part in brackets. And then you see if I put here a 10, sorry, this didn't work. But then you have just the interval between 5 and plus minus 5. Okay, so random variable, we choose just our random generator, and then let's say d0 times random number minus 0.5. Oops, what's happening now? Please do not crash now. What happened? Hopefully it hasn't crashed. So this, no, it hasn't. Good. Okay. This we then also move downwards. And actually, we have to know that always if we click on this series, then he recalculates a random number. And if we want to use one series which we had, therefore I move this just to the right, and then afterwards I will read in the fixed numbers we have created within this time series. You will see this in a minute. So here you have seen it. If always, if I, no, not it's now, but if I press now enter, then always the numbers are changing because he is recalculating a new random process. So again, and then I had to copy this one, and copying here 1 to 3 means that I'm copying. Oh, this you don't see. Why do you don't see this? Oop. Because I'm too. So copying, and now you see it. If you use this paste function, then you see that I have copied the former calculated random functions. Okay, but this we will do in a minute. Let's first just read this in, and Then we will add this also in our time series. And then the yellow line here, we see that this is now our random component. Well, and yeah, maybe in order to say that we want to create a time series which is maybe mainly dominated by the economic trend, we now scale down our gray and our yellow line, and maybe to have a more important impact of our cycle, then we just upscale our cycle. So let's use here 1.5, and let's use for the season, let's say 0.3 maybe, and for the random component, let's say not 10, but only 2 maybe. Okay. So, and now we just create our total series, and this we just add up all. This, so the trend data plus the cyclic data plus the seasonal data plus our random data. And let's take the total one and also read in the data itself. And this blue line, let's change this just to red maybe. Oh, contour this one. Okay. So then the red line here is then, so to speak, our real data with all these components you have. Well, of course, and in reality, it is of course the other way around, that we have the red line. This is our data from our company. But then hopefully you can imagine that in statistics you are going then the other way around. So we then more or less say that putting all components together we obtain a function that we have xt equals at times e to gamma t plus bt sine of what did we have, 2 pi t over small bt plus well, how should I create this one here? Yeah, well, let's call this C 1 to 4, so that we just add always these numbers here. 0 to 3 it is. And plus, and the random component, which we here artificially created, is then in reality, of course, some error parameter which we have. Well, and what we have then now is, here is 1, 2, 3, or sorry, this should be, of course, a fixed number, of course, all this. So 3, 4, and this is then 5, 6, 7, 8. So what we have then is an 8 parameter function. And of course, what we have done in the first part of this lecture was that we chose just a function, a linear line, as our fitting function for our data. And of course, what we also can do is that we just use more complicated functions, and that again, we now start to vary these 8 parameters just in a way that we are hopefully as close as possible. And then we also can again discuss, we want again to minimize the sum of the squared distances from some some theoretical function with respect to the red line. And this would be then, in our case, here artificially created. Let's move this again here. This would be then total theoretical. This would be then just the function without the error term. Okay? So this plus this plus this. And let's read in this also. And now you see, of course, that we have a difference between the green time series and the red time series, because the red time series, there we are adding the random component. And now what you can think of is, I'm now trying to vary my 8 parameters in such a way that the green function is as close as possible relative to some measure, and there we quite often choose these squared distances in order to minimize, again, not with respect to a simple line or a plane in the multilinear regression, but here with this somehow complicated exponential sign plus some seasonal component function. And then you get more or less from your statistical analysis, you get out numbers for your 8 parameters which with which I created here my theoretical part of the function. And then although if you look at the red line, you have here, very different fluctuations within your data. In the end, then you can make a statement as the president of your company. Of course, from my data, I have identified a growth rate here of 5% out of my historical data. And if I'm then forecasting it, that I say, well, I do not want to change very much in the future within my company. Okay. Well, of course, what you aren't allowed to do is to do it the other way around. And well, there are unfortunately very famous examples where guys have done this the other way around. And one of these guys was a highly recommended physicist, a German physicist. He was done his experiments, and he was also, within the persons who maybe should obtain the Nobel Prize in physics, because he had really very well results in a field called superconducting. And well, after 10 years, one has found out that all his data was created like I did it here. And this was actually found out because he wrote then different papers, and there one found out that the random component of two totally different experiments were the same. And the probability that the random component within two experiments are the same, especially if these experiments are totally different from each other, then of course one found out that he cheated because he just more or less created the data like this. But on the other way around, in understanding how these components are sticking together, then I think one gets a feeling how one can get out the information of then true data. Okay, that much for today.